All right, so I only have 3 slides. The thrust of the argument is that can you essentially use heat fluxes to develop logic devices? So if you were to do that, first you'd have to make a transistor. And the concept of a transistor is that it allows the flux to go in one direction. You have to make a diode. The concept of the diode is that you allow the flux to go in one direction. So the idea here is to have a material which has particular genomic qualities that allow the heat transfer to go in one direction. So the material then, if you're looking at that board from left to right, would allow heat to go from left to right, but not allow it to go from right to left. As a result of which, it would be a conductor in one direction, and it would be an insulator in the other direction. If you were able to make a diode, you can essentially have circuits of diodes, and once you have circuits of diodes, you can make gates. These gates could be AND gates, NAND gates, OR gates, and so on and so forth. And so therefore, rather than using electrons, what you would do is that you would essentially use heat fluxes to drive logical operations. So think about sustainability. Think about all the waste heat in the universe, not just on Earth, but in the universe. The fundamentals of thermodynamics are that you have a hot reservoir and you have a cooler reservoir. And heat flows from a hot reservoir to a cooler reservoir. So there's always an abundance of heat fluxes in our universe. Geothermal flows are driven by heat fluxes. Atmospheric flows are driven by heat fluxes. There are lots of heat fluxes being driven right in this room from the biological scale to the physical scale. Now, biology does a very good job at directing heat fluxes. So the idea is, why not physical devices? There's only one problem with this approach. The problem is that heat does not flow in discrete quantities. Electrons do. But if you didn't use bulk materials, if you use nanoscale materials, what you can do is you can confine heat. At the nanoscale, heat transfer is nothing but lattice vibrations or the motions of phonons. And so what you can do is you can confine phonons into very, very small spaces. And once you start to confine phonons, they lose their diffusivity. They do scatter, but they lose their diffusivity, and you can make them more focused. And what research has shown is that the genome of a thermodiode is one in which the thermal conductivity is not a separable function of temperature and space. That is, that at any point in that material, you cannot separate out thermal conductivity into a spatial component or a temperature-dependent component. You can make diodes with inhomogeneous materials when you introduce asymmetry. So the first example of this was about 6 or 7 years ago. There was a paper in Science by Arun Majumdar and his group, where they essentially took a carbon nanotube and they soldered a boron nitroid and nitride nanotriangle to it. And what they showed was that because there was spatial asymmetry, the heat flux in one direction was not as large as the heat flux in the other direction. So that was an example of a thermodiode. In the literature, this is also known as the problem of thermal rectification. Now, most of the attempts, starting with Majumdar's attempt about 6 or 7 years ago, have focused on solid materials. So what people have done is, for instance, they have started to dope materials to introduce asymmetry. So for instance, a carbon nanotube might be pure carbon at one end, but you might have carbon isotopes in it. So it's C12 at one end, and as you go along the carbon nanotube, it's perhaps C13 or C14 at the other end. You could dope materials very differently also. You could have silicon-carbon blends in a nanostructure. People have also tried to do this with stress. So for instance, if you take silicon nanowires, and if you twist them, or if you stretch them, what you find is that by applying a differential twisting or stretching, you can change the thermal conductivity in the material so it becomes insulating in one direction and conducting in the other direction. The only problem is that when you do that with solids, these manipulations are much more energy intensive than if you were to use solid-liquid interfaces. So our approach has basically focused on solid-liquid interfaces. So for instance, over here, what you might have is a reservoir. So there's a reservoir. The reservoir is separated by two silicon walls. And so for instance, one wall is hot at a hot temperature, T sub H, and one is at a cold temperature, and that drives the heat flux. Now, separating the reservoirs is a fluid. You can manipulate those solid-fluid interfaces. You can make one interface hydrophilic. You can make the other face, the other face of the solid wall hydrophobic, and by doing so, you can change the heat transfer characteristics. You can have a fluid in which you can apply body forces. So, for instance, if you had a magnetic fluid, which is basically just a suspension of magnetic nanoparticles in a host fluid, or if you had a fluid that responded to electrical impulses, for instance, then you could push the fluid towards one wall or the other wall. And so by manipulating the hydrophobicity of the walls, or by manipulating the external force that you might apply on the fluid, what you can show is that you can vary the heat flux and bias it towards one side or the other. So essentially, the material genome of such a device should have strong binary interactions between adjacent molecules or atoms. And you can program this material on the fly to increase or decrease its thermal conductivity. And that's what we try to do. So for instance, we showed that one can have a thermal diode, or one can have thermal rectification by using these solid fluid interfaces through a couple of papers, one in Applied Physics Letters and one in the Journal of Chemical Physics. So we've shown the feasibility of the concept. And right now, there's a paper under review in which we've shown that one can actually make a transistor. So here's the concept of the transistor. It's a busy slide, but I'll basically show you what the concept of the transistor is. You have an input where there's a heat flux. You have an output where you withdraw the heat flux. And then you have a gate. With the gate, you provide an additional heat flux or you extract a heat flux. And that's basically a three-terminal transistor. When you vary the heat flux at the gate, you can now automatically vary how much heat flux comes in or how much heat flux is extracted. When you do that, what you will find on that busy slide in the top left-hand corner is you can define certain threshold temperatures, whereupon, as you vary the gate temperature, the input heat flux either goes up or the output heat flux goes down very dramatically. And so again, this is essentially a heat flux that can be driven by a gate temperature. When you drive a heat flux with a gate temperature, you have a transistor. If you define an input or an output as something that drives something else, you now have a transistor. Once you have a transistor, and if you can allow those transistors to occupy a circuit in series or in parallel, you can now start to drive logic operations. We have eager funding based on the funding we received from the National Science Foundation. It's a very small $100,000 grant. But I also submitted this concept to the EFRI community panel for the 2014 EFRI competition. There were 140 EFRI submissions. 16 were selected for presentation. The presentations were about 25 minutes. Out of them, 6 were selected as finalists. This was one of the finalists. But I don't think this is going to make one of the final 3 or the final 4, because the ultimate criticism was it's a very novel idea, but we don't really see a pathway to engineering, that is to development. So I think if given time, and if I'm smart enough to think of how one can develop this idea, it might have legs. So that's basically the thrust of my presentation. Thank you.
Any questions?
Well, I think this is great work, and I think if you get some top-notch physicists to work with you, maybe they'll find a way to use it. Okay.
And given my circumstances, it's win-win. If somebody at Virginia Tech wants to take this and run with it, you could have an international collaboration.
We will. And we'll shoot the breeze in Niagara Buffalo.
At Buffalo, Niagara Falls. I'm off to Canada in July to be the Dean of the Faculty of Engineering at McMaster University, which is in Hamilton, Ontario. So,
Congratulations. Didn't know that.
So if somebody wants to run with this, it's your intellectual property from now on. It's funded by AAS.
Do we get your money?
Yeah. There's some leftover DSM. I have no reason.
I'm sure they would. All right. Let's thank our the last group of speakers here, and we have a short break, and then Dennis will kick things off for the renewable materials thrust at 4 o'clock. Quick break.
And I'd be happy to write.
It's about an hour south of John's. About an hour and a half.
Yeah, I just.
Okay.
Congratulations. Star rising continuously. We still get to send you there for some reason. Okay. All right. I just want to make sure. And I will check to make sure I send you the right chart. Okay. And we think we just have to worry.
Hey, the ESM job is open. It's a great job.
No, it's not actually
Everyone's been.
It's like a total.
hang up with software distribution, so we cleared that up and everything should be installed.
You can't tell the differences anymore. You really can. You take like some of we don't know what we want anymore. We just solve problems.
Hey, Carl, I just sent you a note on that study abroad proposal. Basically, global was
Okay, I'll do it. It's not a problem. Which is the idea.
It just looked like an isolated research project.
No, it's fine.
I just sent you notes that
Okay,
I think that's
okay, I'll do it again.
Okay, yeah, it should be simple.
Okay, excellent. Actually, one of the reasons because we do it with them is because the biosciences program has all the areas that the biology